Welcome to The Explainer. Today we are embarking on a massive, planet-spanning geological detective story. We're going to connect the deep-time history of our Earth, processes that literally happened billions of years ago, directly to the future of clean energy and the very devices you use every single day. We're piecing together clues from deep within the Earth's mantle to solve one of the absolute most pressing resource puzzles of our modern age. So get ready, because you are about to look at the ground beneath your feet in a completely new way.
Okay, let's dive into this because it presents a genuinely mind-blowing paradox. How in the world does a tectonic plate collision that occurred long before complex life even existed on Earth have anything to do with a smartphone right in your pocket? I know, it sounds like pure science fiction, but it's real, cutting-edge science. To understand the technology of tomorrow, we actually have to look backward, deep into the geological record, to uncover exactly how our planet prepared the specific ingredients we now desperately need.
And that brings us to the first major clue in our mystery, the critical mineral problem. As we push forward into this high-tech, environmentally conscious era, we're rapidly transitioning toward green energy and advanced electronics. But we have a massive bottleneck. You see, the materials required to build this future aren't just lying around everywhere. We are facing an urgent global challenge to source the highly specialized minerals that actually make the whole green transition possible.
Think about it. Every single one of these modern marvels, electric vehicles, wind turbines, smartphones, and even complex defense systems, is fundamentally dependent on a specific group of materials known as rare earth elements, or REs. Our reliance on them is absolute. But here's the kicker. Despite the name, rare earth elements aren't actually all that rare in the Earth's crust. The real global nightmare is finding them concentrated enough to form economically viable deposits. Locating a spot dense enough to actually mine is incredibly difficult. They are the ultimate hidden treasure.
So if we're hunting for a highly specific hidden treasure, we need a prime suspect. And in the world of geology, our prime suspect is an incredibly bizarre, highly prospective, and deeply anomalous type of rock. To find the rare earth elements we need, we have to track down literally some of the weirdest and rarest rocks our planet has ever produced.
Let's break down this definition from the Geoscience Canada Review, because this right here is our prime suspect, carbonatite. In academic terms, it's an unusual igneous rock containing more than 50% carbonate minerals. But let's strip away the jargon for a second. Most magma, like the stuff you see erupting from typical volcanoes, is based on silica. It's thick, it's sticky. Carbonatites are completely different. They are carbonate-based magmas with a very low viscosity, meaning they are incredibly runny. They can migrate rapidly toward the surface from deep within the Earth. And because of their highly unique chemistry, these magmas act like ultimate treasure chests, sweeping up and hosting massive concentrations of critical minerals like niobium and rare earth elements. All right, so we know what we're looking for, carbonites. But where on Earth do we find them? They are incredibly rare, representing just a tiny fraction of rocks on geological maps. And this is where a major breakthrough from a research team at Adelaide University completely changes the game. They've essentially handed us a treasure map for modern explorers by looking back 2 billion years into Earth's geological history. They found an ancient tectonic clue that tells us exactly where to look right now.
Now, what's really interesting about this is how the thinking has totally shifted. For a long time, the dominant theory was that these valuable deposits were primarily linked to mantle plumes, massive columns of hot material rising straight up from deep within the Earth. But the Adelaide University researchers used advanced plate tectonic modeling and proposed something completely different. They discovered a strong global link between these deposits and ancient subduction zones. Those are the areas where tectonic plates violently collided and one plate was forced down beneath another.
The evidence here is just striking. When the researchers mapped out regions of the Earth's mantle that have been altered or fertilized by these ancient subduction processes, the numbers absolutely spoke for themselves. 67% of all carbonatites and 72% of all rare earth element deposits formed over the past 1.8 billion years sit directly over these subduction-fertilized mantle regions. That is simply way too high to be a coincidence.
So, the crucial point is what happens when we look even deeper into the past. For older deposits, that correlation doesn't just hold steady, it skyrockets. A staggering 92% of older deposits perfectly correlate with these ancient tectonic collisions. The fluids and elements released when one plate gets crushed beneath another act as the fundamental fertilizer. It creates the perfect conditions for rare earth deposits to eventually form.
But hey, there is a wild twist in our detective story. These ancient tectonic collisions did not turn into critical minerals overnight. If a plate collided 2 billion years ago, it didn't just instantly sprout a rare earth element deposit on the surface. Instead, this process required a massive, deep earth incubation period. It's a highly complex, two-stage process characterized by a massive time lag that left even the researchers completely surprised.
Think of the Earth's mantle like this highly secure, incredibly patient vault. Around 2 billion years ago, you have the initial event. A subduction zone forces the tectonic plate downward, releasing fluids that fertilize a specific zone in the mantle. Then comes the waiting game. For hundreds, sometimes literally billions of years, this enriched zone just sits there in the mantle vault, perfectly preserved. It isn't until a completely separate geological trigger event occurs, sometimes much later, like 1.8 billion years ago, that this specific region finally melts, forms that runny carbonate magma, and shoots those critical minerals up toward the surface.
As Professor Carl Spandler, who led this research, perfectly summarized, this research shows that the ingredients for these critical mineral deposits were put in place many million to even billions of years ago. And this brilliantly illustrates how this completely rewrites the timeline of how our planet prepares its resources. The wealth was deposited into the Earth's vault eons ago, just waiting for the exact right conditions to be released for us to find today.
So how does knowing about 2 billion-year-old tectonic crashes actually solve our modern exploration problem today? Well, if you're a mining company or a geologist tasked with finding the raw materials to build millions of wind turbines and electric vehicle batteries, you no longer have to wander the globe blindly. You can literally use the planet's ancient history to search for our technological future.
By mapping out these ancient subduction zones, scientists have given explorers an incredible tool. These fertilized regions cover approximately 35% of the Earth's continental crust. Now sure, 35% might still sound like a huge amount of ground to cover, but compared to searching the entire planet at random, scientists now have a vastly narrower, highly accurate map to focus their exploration. By knowing exactly where these ancient collisions happened, we dramatically increase our chances of making those future discoveries.
Let's move forward and see how this builds, because the Earth is incredibly dynamic. Co-author Dr. Andrew Meredith highlighted a critical nuance here. Over billions of years, continents crash together and pull apart multiple times. The research found that in areas where multiple subduction events overlapped, meaning a section of the mantle was fertilized not just once, but over and over again by different collisions, you find the absolute highest, richest concentrations of rare earth element deposits. It's like finding a spot on the map where treasure was buried, and then someone else came along and buried a whole bunch more treasure right on top of it.
Which leaves us with one incredibly profound question. What other vital resources might be hiding right now in Earth's deep time history? Every modern convenience we rely on, from the phone in your hand to the clean energy grid of tomorrow, is deeply, intricately tethered to violent tectonic collisions that happened billions of years ago. By understanding our planet's ancient past, we really are unlocking the keys to our future. Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll catch you next time.